Welcome everyone, I'm Marco Paolieri from the University of Southern California and I will present our ICP 2020 paper, Throughput Prediction of Asynchronous Stochastic Gradient Descent in TensorFlow. This is joint work with Zhuojin Li, Wumo Yan, myself and Professor Leana Golubchik. The context of our work is that of distributed systems for deep neural network training. Deep learning has achieved breakthrough results in several application domains, including computer vision, speech recognition, and natural language processing. In contrast with traditional machine learning, deep neural networks, or DNNs, are able to discover internal representations of the input data without the need of manual feature engineering. This approach requires very large amounts of training data and very large amounts of computation. For example, DNNs for image classification have millions of parameters, called weights, which are adjusted during training using millions of labeled images. These training images are processed in batches using stochastic gradient descent, an optimization algorithm to adjust the weights of the neural network so as to minimize the number of misclassified images. The training performance of stochastic gradient descent can be improved by scaling up using more powerful hardware, especially GPUs. In the slide we see a photograph of the NVIDIA V100 GPU. But to improve performance even further, one can use multiple worker nodes. To train with multiple workers, the parameter server architecture is a popular solution. The parameter server holds a global version of the neural network weights, while each worker receives this global version, computes an update to the weights locally, processing a batch of examples using stochastic gradient descent, sends the update to the parameter server, and finally the parameter server applies the update to the global version of the weights. We refer to these four phases, which are repeated over and over for several batches of training images, as downlink, computation, uplink, and update of the global model. In asynchronous stochastic gradient descent, there is no synchronization between the workers. The parameter server applies updates from the workers as soon as they are received, which can create different interleavings over time of the workers exchanging data with the parameter server. As we increase the number of workers, we expect the total number of examples processed in our cluster, which we call throughput, to increase as well. But throughput scales only sublinearly and actually saturates as we increase the number of workers. This happens because worker nodes saturate networking to and from the parameter server. The figure on the right shows the throughput in a cluster of 1 to 10 worker nodes on AWS. We see that throughput saturates, and when worker nodes use more examples in a batch for stochastic gradient descent, computation takes longer at these workers. They access the network less frequently, so there is less load on the network and saturation happens later. Our goal in this work is to predict throughput for any number of workers from a quick single node profiling of a training job. This is particularly important when multiple training jobs share a computer cluster and a scheduler needs to decide how many nodes to assign to each job, depending on the amount of work that each job has to perform, and also on how efficiently the job can use the nodes. For example, here we see that the training job with batch size 128 is highly inefficient when more than 7 worker nodes are assigned. We've studied this problem in the past, and in particular in our previous work at Mascots 2018, we developed a queuing model using the mean time for downlink, compute, uplink, and update phases, which we estimated from network traffic measurements during single worker profiling. But we noticed that this model was inaccurate for some deep neural networks, especially using modern machine learning frameworks such as TensorFlow, and other approaches such as Cynthia, also based on coarse high-level analytical models, resulted in similar mispredictions. We investigated this problem and realized that in fact computation can have a significant overlap with communication during asynchronous stochastic gradient descent for some deep neural networks. So a coarse model where each worker goes through each phase, downlink, compute, uplink, sequentially, is not sufficient. The time between what we see on the network as the end of the downlink and the beginning of the uplink is not the computation time. In fact, the first part of the computation, the forward propagation in red, starts well before the end of the downlink in yellow, and the second part of the computation, backpropagation in blue, continues during the uplink phase. The reason for this is that model parameters, the weights of the deep neural network, are not transferred as a single message from the parameter server to a worker, but they are split into multiple tensors, each used for different operations at different layers of the neural network. As soon as the tensors needed to perform the first operation are received from the downlink phase, computation can start, while tensors needed for other operations are still being transferred. So we can describe a distributed training step as a dependency graph, like the one in the bottom right figure here, where computer operations in red depend on the downlink of different tensors in yellow, and uplink in green depends on other compute operations in blue, and finally the update at the parameter server depends on the uplink of such tensors. And what we're showing here is a very simplified view. Real deep neural networks include hundreds or thousands of these elementary operations, and previous models, we believe, overlooked the complexity of communication and computation in asynchronous distributed stochastic gradient descent. In this work, we take a different approach. Using the profiling tools of TensorFlow, we analyze the computation graph of a deep neural network training job, and in particular, computation and communication operations and their mutual dependencies. Then we record in a single worker configuration a trace of start and end times for these operations over many training steps. To predict throughput with multiple workers, we use this recorded trace to sample steps for each worker. Of course, now workers are sharing the network, so the duration of concurrent data transmissions is extended to account for the reduced bandwidth, and as a consequence, dependent operations can be delayed. But there are some challenges in doing this. TensorFlow has profiling tools, but these tools record the time when the sender requests a transmission or when the receiver is notified of the reception of the entire message. These times are not the same as the beginning and the end of data transmission over the network. In fact, to transmit data, TensorFlow uses gRPC, which is a library for remote procedure calls. And the API of this library is asynchronous. Requests made by the sender are queued, and many requests can be served in parallel by sharing a single HTTP2 connection. And they can be stopped and resumed over time. So the time interval between the sender's request and the receiver's notification is not an accurate representation of the transmission time for a message. And even with a single message, with a single transmission starting immediately, notification of the receiver is delayed with respect to the end of the transmission because of data deserialization and memory copies after the data is received. So this is very complex, but on the other hand, we do need to know when transmission is happening, because when we generate synthetic traces with multiple workers, the duration of transmissions should be extended when they overlap and share network resources to and from the parameter server. To develop a model of communication overhead at the end of a transmission, we measured parsing overhead for transmissions with varying data size. And our measurements clearly suggest a linear model of overhead time as a function of data size. The parameters alpha and beta depend, of course, on the specific platforms, including CPU speed, memory bandwidth, and operating system, but they can be estimated once for a cloud VM type or physical node, and then used for throughput prediction of any training job on that platform. Understanding the multiplexing of transmission streams during downlink and uplink was more difficult. gRPC uses HTTP2, which in turn multiplexes several streams in a single TCP connection between the parameter server and a worker. The receiver side can advertise a flow control window, the amount that the receiver is ready to receive, but the management of this parameter and the scheduling of different streams are all implementation dependent. And things can be quite surprising. The figure on the left shows how downlink transmission from the parameter server to a worker node alternates between different streams, numbered on the y-axis. We generated this figure by capturing the network traffic with TCP dump during one training step of the AlexNet neural network and analyzing HTTP2 frames in the captured traffic. We observed that in the implementation of HTTP2 used by gRPC, streams smaller than the flow control window are transmitted until completion and exclusively. For larger streams, after transmitting a control window of the stream, this implementation switches to the transmission of other streams. But this preemption happens only once. When the large stream is selected again, it is transmitted to completion, irrespective of the size of remaining data. That's why we see those long horizontal lines where a single stream is being transmitted for a long time. So to decide which tensor is currently being transmitted, we do the same. We look at the size of each tensor, and when the tensor is first selected for transmission, we send up to a control window, about 28 megabytes, and the next time that the tensor is selected, we simulate the transmission of the rest of the data. We tested this model on the downlink phases of 100 training steps, comparing predicted end times with measured end times. And we repeated this for different deep neural networks on our cluster and on AWS. The measured error was about 1 to 2% on our cluster and higher on AWS, 3 to 4% for all models except Inception v3, which is the deep neural network with the most tensors transmitted simultaneously, and we believe this is the reason for the higher error in this case. Also, we observed that multiplexing and switching from one stream to another can be counterproductive. Ideally, we should prioritize the transmission of those tensors that are unsatisfied dependencies, preventing the execution of the next compute operation. In fact, this is what another research work does by analyzing the critical path in the computation graph. The work is called Tic-Tac and was presented at CSML in 2019. Given that this is something important for high-performance distributed training, we also test our prediction methodology when multiplexing is disabled, using different policies for the scheduling of tensor transmissions, including Tic-Tac. So in our approach, given a system configuration including network bandwidth, number of worker nodes, number of parameter servers, and parameters of the communication overhead model, we simulate a sequence of stochastic gradient descents with an arbitrary number of workers by sampling steps with replacement from the profiling trace collected in a single worker configuration. Each worker replaces the sample step, which is a graph of communication and computation operations with dependencies, but while computations at each worker have the same duration as measured in the sample step, instead, the transmission of each tensor is scheduled using our multiplexing model, and at the end of the transmission, we add parsing overhead. When the parameter server is transmitting to multiple workers or vice versa, bandwidth is shared equally. We use 3 platforms to validate our approach: a private cluster of 8 nodes with quad-core processors and 1 gigabit per second Ethernet, clusters of AWS C4 8x large instances, also CPU only but with 36 cores and 10 gigabit per second Ethernet, and clusters of AWS P3 2x large instances. These have 8 cores but one NVIDIA Tesla V100 GPU, the most performant GPU for deep learning, and are connected with 10 gigabit per second Ethernet. For each platform, we estimate the parameters of our communication overhead model. Then for each job, we run 100 steps with one parameter server and a single worker node to obtain the trace of operations and their dependencies for the specific deep neural network. To predict throughput, we run our trace simulator with 2 to 7 worker nodes for 1000 steps, and we evaluate the mean throughput along the trace. In fact, we skip the first 50 steps to allow workers to get out of the initial synchronization. To validate our prediction, we run clusters with 2 to 7 workers on AWS or on our private cluster, skipping the first 50 training steps and measuring mean throughput on the next 50. So in our private cluster, first on the left, we validate on a given deep neural network, AlexNet, for different batch sizes. Our predictions in blue are close to the actual measurements in green. The error is at most 10% and consistently lower than alternative prediction approaches in yellow and gray. Next, on the right, we validate on different deep neural network models, including GoogleNet, Inception, ResNet 50, and VGG11. Prediction error is also within 10%. In addition, we explored the effects of HTTP2 stream multiplexing on our predictions. First, on the left, by turning off flow control and multiplexing for different deep neural networks. Then, on the top right plots, by enforcing different orderings, the tick ordering, the reverse of that, and a random ordering with AlexNet. And finally, in the bottom right, enforcing the tick transmission ordering of tic-tac on various deep neural network models. Without multiplexing, communication is more predictable, and the error of our predictions is even lower, at most 5%. Next, we validate our approach on the Amazon Web Services cloud platform. This environment is less stable than our private cluster because networking performance can be affected by background traffic or by the deployment of VMs to different racks. In this environment, communication overhead due to parsing of received data is much more significant because networking is 10 times faster. So if parsing overhead was 10% with 1 gigabit per second, now with 10 gigabits per second, it becomes 53% of the transmission time. So very relevant. In most cases, our prediction error is now within 20%, and this is better than alternative approaches. Our last validation platform is that of AWS VMs with NVIDIA V100 GPUs. In this case, the error is within 20% for most DNN models, batch sizes, and number of workers. In some cases, though, the error is higher, within 30% for the case of 4 workers in figures A and F, or 3 workers in figures J and K, and within 40% with 3 workers in figures E, L, and M. This is only for a few configurations, and these higher errors occur in scenarios with few workers and small batch sizes, which result in short computation times. In these cases, it is difficult to predict the interleaving of communication between different workers and the parameter server. Finally, we validate our approach on AWS in settings with 2 parameter servers. In the plots, we report our predicted throughput with 2 parameter servers in blue and the throughput measured for 2 parameter servers in green. We also report the throughput measurement for 1 parameter server in purple to highlight the fact that throughput is indeed improved when the networking load is split among 2 parameter servers. Prediction error is within 20% for most DNNs and settings, 25% in some cases. Note that for VGG11 in figure H, throughput is only marginally improved when adding a second parameter server. This happens because data is not split evenly among the 2 parameter servers. Since our method is based on real profiling traces collected in a configuration with 2 parameter servers and a single worker, we account for the uneven split and correctly predict the throughput. Finally, it is interesting to analyze the savings enabled by our predictions. After all, instead of predicting throughput of a training job, one could perform several measurements, one for each number of workers, and provide the results to the scheduler assigning nodes to the different jobs. We compare the execution time and cost of our prediction approach for different deep neural networks and batch sizes using C4 large AWS instances with 2 CPU cores for our simulations. In contrast, measurements require GPU instances, which are over 30 times more expensive, and they require these instances for longer periods of time to collect measurements, because actual DNN training is running, not just a discrete event simulation. So, prediction allows both faster evaluation and cost savings. In conclusion, our work proposed an approach to the prediction of training throughput of asynchronous stochastic gradient descent in TensorFlow. This approach extracts tracing information from minimal single worker profiling and performs discrete event simulation to generate synthetic traces with multiple workers. Experimental results show good prediction accuracy across DNN models, batch sizes, and platforms, as well as implementation variants of TensorFlow, including networking optimizations. Although this simulation-based approach outperforms existing analytical models, we find that for future work, it is still of interest to develop more fine-grained analytical models, allowing overlap of communication and computation.